Good morning and welcome back to Dr. Logic Awkwardly Does Logic. In my previous video, I defined system S5 as system T plus axiom E. But what is axiom E? Other than the other of the stronger of the two reduction principles that T didn't have that we could add to T. That's what I want to talk about in this video. So let me get up the whiteboard because we're going to be doing some correspondence results. First of all, recall what the axiom is. The axiom is, if P is possible, then it is necessarily possible. This axiom, the reason it's called E is because it corresponds to a frame condition which is called Euclidean. The Euclidean condition says that for every X, for every Y, and for every Z, if we have that X can see Y and X can see Z, then Y can see Z. So why is this Euclideanness? Draw a little picture. You've got X and it has a potentially splitting future path, and Y, R, Z, and because this is universally quantified, this means we have both this and this. The Euclidean condition essentially takes a branching path and forms it into a triangle. Euclid likes geometry, triangles are geometric. There you go. Euclideanness, just think triangles. So what we want to do is we want to show that this axiom corresponds to this condition. This means that if we have a frame F that is Euclidean, so it satisfies this property, then we know that axiom E is going to be valid on this frame. So it's always going to be true that possibly P implies necessarily possibly P. And if we have an F that validates possibly P implies necessarily possibly P, then F is Euclidean. So these, you'll recall, are the two things that we need to prove in order to prove a correspondence result. So let's start off with this direction. This is the easy one. We suppose that F is Euclidean, and then for contradiction, that it doesn't validate the axiom. So we don't have possibly P implies necessarily possibly P. If the axiom is not valid on the frame, this means that there is a model M on that frame and a world W such that on that model at that world, the axiom is false. So let's just move away from describing this in words and start building what the model would look like. We've got our W here, and we want to show that possibly P implies necessarily possibly P is false. That's the same thing as saying possibly P is true and necessarily possibly P is false. Now, if we have a true possibility, this means that there needs to be some world W prime over here where P is in fact true. If we have a false necessity, that's the same as it being possibly necessarily not P. So all we've done is we've taken this false, we've turned it into a true statement by sticking a negation on the front and then driving the negation through. This is another possibility, so we need to create a new possible world, W2 prime, where at this world we will have necessarily not P being true. But look at this. We assumed that our frame was Euclidean. We have a world that can see two worlds. This means they need to be able to see each other. But as soon as W2 prime sees W prime, the fact that not P is necessary here means that not P has to be true over here, which means P has to be false. And there is our contradiction, because then P has to be both true and false at W prime. Therefore, if you have a Euclidean frame, you cannot falsify the E axiom. Let's move on to a new board for the other direction, which is that if we have a frame that validates the axiom, then that frame is Euclidean. We're going to prove this one contrapositively. That is, if we have a frame that is not Euclidean, then we can find a model that falsifies the axiom on that frame. So what would a frame that is not Euclidean look like? There's many different things. It could be reflexive, it could be irreflexive, it could be transitive, it could be non-transitive. But the important thing is that we have this branching split where I'm going to just change to a different color so you can see we don't have an arrow that way and we don't have an arrow that way. One of those has to fail. It doesn't matter which one because the argument will be symmetric either way. So we've got a frame that looks like this. Define a model as follows. At the world that is not seen, here, I'm going to label this one W. So we've got these two worlds. At least one of them is not seen by the other one that W sees. So we have to phrase it this way because there could be many other things going on in this frame that I haven't drawn. But we know that there is one of these two worlds is not seen by something that W sees. So at that world, let the value of P be true. Let the value of P be false at every other world. So suppose that, let's do it similarly to how we had it on the previous one. This is the world that is not seen by the other world that W sees. So we make P true here, and then P false, and any other worlds that we haven't drawn, it will also be false there. Then we know that possibly P at W is true because W can see this world here where P is true. We know that necessary not P is true at this world because everything that this, either this world sees nothing, in which case the necessity claim is trivially true, or whatever else it sees are all things where P is false. So P is necessarily false. So this means that necessary P at this world, now I suppose I should give it a name, so let's call it W prime. It's going to be true, but that makes possibly necessary, this should be necessary not P. This makes possibly necessary not P at W true, which is the same as saying that on this model at W, necessarily possibly P is false. And there we go. We have a model that whatever non-Euclidean frame you have, you can build this model and it will make the formula false. So if the frame is not Euclidean, then the frame is not valid. Therefore, by contraposition, if it is valid, the frame has got to be Euclidean. So this shows you a bit more about what this axiom is. What does it do? How does it interact with frames? Gives you another example of a correspondence proof, which is something that we haven't seen in quite a while, but it's a very useful thing to be able to do. And it also explains the meaning of the name E. It's E for Euclidean, and Euclidean is triangularity. So there's that. Now, I also promised you that we would have an alternative axiomatization of S5, and that will be the topic of next video. So join me then. Until, take care.